Welcome. Before I begin today, I'd like to tell us that all our classes will be based on the Nigerian Senior Secondary Curriculum or the West African Senior Secondary Curriculum. So we cover the WAEC syllabuses, we cover JAM syllabuses, and then we cover NECO syllabuses. So today we are doing mathematics. The topic is number bases. Alright, so whenever you hear number bases in mathematics, it means the number of items that form a bundle. In any counting, let's say you have 10 items to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you have to do your counting in base 3, for instance. It means that out of these 10 items, when you count 1, 2, 3, you have one bundle. 1, 2, 3, another one bundle. 1, 2, 3, another one bundle. And you'll be left with one item that is not up to 3 again to form another one bundle. Alright? So if you are counting 10 items in base 3, you are going to have 3 bundles, remainder 1. So we call it 3, remainder 1. And if we're doing addition of the number bases or the addition of the numbers, once you have these 3, you take it to this other side while you drop the one that's not up to a bundle on the line. Alright, so if you have to count this also in base 4, for instance, so you count 1, 2, 3, 4, that's one bundle. 1, 2, 3, 4, another bundle. Then this 2 is not up to a bundle to give you another, it's not up to 4 to give you another bundle. So if you are counting 10 items in base 4, you are going to have 2 bundles, remainder 2. So number basis simply means the number of items that form a bundle. It is important for us to have this introduction so that you would bear this at the back of your mind so that going forward you are going to be applying that simple rule. Alright, another thing I would like us to know about this topic is that you cannot have this kind of a number, let's say 10201 there's 2. It cannot exist. Why? Because there's a rule that says that if you have a particular number in a particular base, all the digits of that number must be less than the base. But here you see we have a digit that is up to the base. All the digits must be less than the base. If you have a digit that is up to the base or even greater than the base, it means that number cannot exist. It is important for us to mention this because while solving these questions under this topic, you might have an addition of a number, you land your final answer at this. This will automatically tell you that your answer is wrong because it is violating the rule, which is that a number in a particular base cannot have any of its digits equal to that base, let alone greater than that base. So all the digits must be less than that base. So if you have something like 101101111 x2, this one is correct. This one can exist. Let me use that word. It can exist. Alright? But this one cannot exist. Okay. Having said that, I'd like us to know also that base 2 is also a very popular base. It is called the binary. Alright? We also have some other popular bases like base 8 is called the octal, or you call it octal number. Base 9 is called the nonal. And then base 10, which is called denary or decimal. Base 10, which is called denary or decimal, is a central base. We refer to it as a central base, or you call it a reference base. As we go further, we are going to see what we call base 10 a central base or a reference base. Alright, the subheading I want us to look at now under number bases is converting from base 10 to other bases. I just want to write it in short like that. To convert any number in base 10 to other bases, what we do is the table method. So an example is if you have 73 base 10 and you are asked to convert it to base 2, which is called the binary. For example, the method is the table method, and this is the table method. The number you are asked to convert, you put it on the right hand side. The base you are converting it to, put it on the left hand side. So we have, the question is convert 73 base 10 to base 2. Alright, this is a very basic example, but as we go further, we'll be introducing some complex or more complex questions under this topic, number bases. So the approach is very simple. Take note, when you are converting from base 10 to other bases, you use what I call the table method. But if you are to convert from other bases to base 10, you use what I call the linear method. So here the approach is to just use this number and be dividing this one after the other and dropping your remainder. So 2 into 7 is 3, remainder 1. So the 1 is added in front of the 13. That the front of the 3, that gives it 13. So 2 into 13 is 6. Remainder 1. So put the 1 out here. 2 into 36 is 18. Remainder 0. 2 into 18 is 9. Remainder 0. 2 into 9 is 4. Remainder 1. 2 into 4 is 2. Remainder 0. 2 into 2 is 1. Remainder 0. And then 2 into 1 is 0. Remainder 1. Because 2 cannot go into 1. So whenever you are doing your division and you find out that diagonally like this, from left to right like this, you have the same number, and diagonal like this, from right to left like this, you have zeros. That shows the end of your division, and you take your answers from bottom to top. Alright, so you will conclude by saying therefore 73 base 10 equals to, this is how you take your answer. Take it from here, 1 0 0 1 0 0 1. So it's going to be 1 0 0 1 base 2. So that is how you conclude. You are solving in theory, for instance. So 73 base 10 gives us 1 0 0 1 0 0 1 base 2. So now we are looking at how to convert number from other bases to base 10. So in this one we are using what I call the linear method. Quickly, an example is this one I want to give you here. We have 177 base 8 to base 10. So let's look at this example. The approach is just write the number out like this and the base like this. And because this is a whole number, alright, the last digit here is called the unit digit. This one is called the 10 digit, and then the 100 digit. So you start from the unit digits and give them powers. So the powers will be increasing from right to left. So power 0, power 1, power 2. So the approach is we take each digit, multiply with the base, and raise it to this power. It's only the base that will raise to that power. So you have 1 times 8 raised to power 2. After each multiplication, we introduce addition. Next is 7 times 8 raised to power 1. Plus next is 7 again times 8 raised to power 0. So this is how to do it. 8 squared is 64. 64 times 1 is still 64. Plus 8 to power 1. Anything raised to power 1 is still that thing. 8 to power 1 is still 8. Alright? So you can now say 7 times 8, it gives you what? 56. Plus 8 to power 0. Anything to power 0 is 1. So 1 times 7 is 7. So we add up everything. 64 plus 56. And then plus 7. That gives us 127. 127 base 10. So we can conclude by saying therefore 177 base 8 equals to 127 base 10. Another example is this one. But in this case, this is a decimal number. Alright, in a decimal number like this, you have to convert 12.55 base 8 to base 10. So we just write it out, 12.55 base 8. In the case of a decimal number like this decimal point, this decimal part, this is the whole part. And before the decimal part, the last digit before decimal part is also the unit digit. So that will still take to power 0. Then it will take to power 1. Still have digits on this side, keep giving them power 2, power 3, and so on. But on the decimal part, you have to power minus 1. Because after 0, the next lower number is minus 1. Then minus 2. You still have other digits, that will be minus 3, minus 4, and so on and so forth. So you now start your multiplication. 1 times 8 raised to power 1 plus 2 times 8 raised to power 0 plus 5 times 8 raised to power minus 1 plus 5 times 8 raised to power minus 2. Alright, so just work this out straight. 8 to power 1 is still 8. 8 times 1 is still 8. Then plus 8 to power 0 is 1. Times 2 is still 2. Plus 5 times, whenever you have a number and a negative power, when you remove that negative sign from the power to change it to a fraction, it will become 1 over that number raised to that power without the sign anymore. Right? But since 8 raised to power 1 is still 8, we don't bother putting 1. Then plus 5 times, here we have 8 raised to power 2. So when we remove that sign from there, it will become 1 over 8 to power 2 this time, only 2, without the sign anymore. Alright? So in the next line, we just add these two together, we have 10. And the reason we can do this addition here, because what is here is still addition, not multiplication. If there was a multiplication sign here, 2 will be multiplied with that. We will not have the power to add to 8 because multiplication comes before addition in Bodmas. So we always apply the rule of Bodmas whenever you want to simplify any fractional expression like this. Alright, so what you do next is plus is 5 times 1 over 8. This is an ordinary number, whereas this is a fraction. So whenever you are multiplying an ordinary number with a fraction, that number has the right to go to only the numerator. So that will be 5 times 1 over 8. So you have 5 over 8. Then plus. Now, 8 squared is 64. That will be 1 over 64. And this is another 5 here. 5 will multiply to the numerator. 5 times 1, so that will give you 5 over 64. 5 over 64. Alright? Okay, having done that, the next thing we are doing is to, since this already stands out as a whole number, we work out the LCM of 8 and 64. Of course, I believe you know, like I said, this class is for the senior secondary students. Those of you who are preparing to do charm and YA. Right? Any student from SS1 should be able to know how to work out, how to use the LCM method to simplify the fraction. So that will become on this side now. Put your 10 here. Then what is the LCM of 8 and 64? So the method is to use this denominator to divide the LCM. What it gives you, multiply with the numerator. So 8 is 64 is 8, right? 8 times 5 is 40. Plus 64 into 64 is 1. 1 times 5 is 5. So your final answer there will be 10 whole number. This plus this is 45 over 64. So your final answer there is 10 whole number, 45 over 64 base 10. So you put there base 10. Alright? There base 10. Equal to 10 whole number, 45 over 64 base 10. So that's your final answer. now let's look at some random questions, which I can also consider to be a little more complex than the ones we have solved. We are asked if 10x1 base 2 equals to 9 base 10, find x. Alright, so this is how to approach this kind of a question. On the left side we have a number to base 2, on the right we have a number to base 10. They are not the same base, so what you should do is that you convert this to have base 10 base 10, or you convert this to have base 2 base 2. So we're going to start from this side. So we're going to convert 9 base 10 to base 2. So to take 9 base 10 to base 2, we use the table method. Remember, from base 10 to any other base is the table method. Alright? From any other base to base 10 is the linear method, the one we just saw previously. Okay, so we put the 9 here and 2 here. 2 into 9, 4 remainder 1. 2 into 4, 2 remainder 0. 2 into 2, 1 remainder 0. 2 into 1, 0 remainder 1. So whenever we have this and this, same numbers here and zeros here, it means that's the end of the division. So we have therefore 9 base 10 equals to 1001 base 2. And we now come to compare that. We put that in place of this 9 base 10. So we now work out that 9 base 10 equals to 101 base 2. So I say therefore 10x1 base 2 equals to 1001 base 2. So how are we going to find x? We are going to find x by comparing the place value. So every other thing here are similar or is similar. This is similar to this. So this 0 definitely is taking the place of x. So we'll say x equals to 0 in that case by comparison. Therefore x equals to 0. So that's how to solve that kind of a problem. Alright, in this other subheading we are looking at how to convert a number that is in a non-base 10 number to another non-base 10 number. That is a number that is not in base 10 to another number that is not in base 10. So this is where I'm going to apply what I told us, that base 10 is called the central base. So whenever you are converting from a non-base 10 to another non-base 10 number, you have to pass through base 10. Alright, so let's look at this example. This example says we should convert 101 base 2 to an octal number, that is to base 8. So we have 101 base 2, we have to convert it to base 8. We can't do it directly, we have to pass through base 10. So that will be 101 base 2 equals to base 10. We get the number in base 10, we convert that number that's in base 10 now to base 8 to arrive at our final answer. So quickly, 101 base 2 to base 8, we take it to base 10 first. So we take 101 base 2. Remember what we did? Unit digits to power 0, 10 digits to power 1, 100 digits to power 2. So that will be 1 times 2 to power 2 plus 0 times 2 to power 1 plus 1 times 2 to power 0. So that will be 2 squared is 4 times 1 is still 4 plus 2 to power 1 is still 2 times 0. That place is gone. Whenever you have anything multiply with 0, it's gone. Anything raised to power 0 is 1. So 2 to power 0 is 1. 1 times 1 is still 1. So you have 5 there. So the answer is 5 base 8. So the next thing is to now convert this 5 base 8 to base 8. Right? The 5 base 8 finally to base okay, this is 5 base 10. We're converting to base 10 first. So now this 5 base 10 to base 8, we use the table method. Put the 5 here, put the 8 here. So 8 into 5 cannot, put 0. Remember that same 5. And I say whenever you have same number diagonally like this and 0 diagonally like this, it means at the end of your division automatically. So that will still equal to 5 base 8. So what's trying to tell us is that 5 is still 5 in base 10 and in base 8. So whenever you have a number in a particular base that is higher than it, that number will remain the same in all the other bases that are higher than it. For example, 5 will remain 5 from base 6, base 7, base 8, base 9, base 10, and so on. It will still remain 5. So we can conclude finally that 101 base 2 equals to 5 base 8 because the digits must be less than the base. So let's quickly look at addition and subtraction of number bases. We just solved some questions under this addition and subtraction of number bases, some random questions, and this can be very tricky at times. This is asked sometimes in JAM, and yet it's something that's also done in primary 4, 5, 6. But what they do, they only concentrate on the binary addition and subtraction of number bases. That is only in base 2. But in the senior secondary, they can give you any base to add or subtract. Alright, so let's quickly look at this first one. We have 1101 base 2 plus 110 base 2. 1101 base 2 plus 110 base 2. So what we just do is align them. This is a whole number, this is a whole number. This is the unit digit, this is the unit digit. So you start, you align them according to their place values. So 0 will come here, this one will come here, this one will come here, and there's nothing here. Put your addition here. It's base 2. Alright, so you 1 plus 0 is 1. Put it here. And I want to bring to your notice, whenever we are dealing with a particular base, remember when we introduced the topic, we said the number of items that form a bundle is called the base. So now we are dealing with base 2. Anytime we add anything that is up to 2, that is one bundle, we are going to carry it over to this side. Right? If it's up to 2 and above, when we take the one bundle, whatever is left, we drop. But here, 1 plus 0 is 1. It's not up to the base we are working with. So we can't form a bundle, so we drop it like this. Another is here, 0 plus 1 is still 1, we drop it. Now, 1 plus 1 is 2. It's equal to the base we are looking at, so you can form a bundle. So we form a bundle, take it over to this side and drop 0 that is left. 1 plus 0, 1 plus the 1 we have brought up, because whenever you bring it up, it's coming as a bundle. It's coming as one bundle. So you add it to this, it gives you 2. And that's another bundle. So what you do, you round it up and take it as one bundle and drop 0 here. So the 1 comes to stay here. So this is what you are going to have when you do this addition. 10011 base 2 will be your answer. So before you watch me solve this one, I'd like you to just pause it and try solving it by yourself, so that when you solve it by yourself, keep the answer. When I finish solving, you look at it and check if you got it right. Alright, so just take this as class 4. 1111 base 2 plus 1011 base 2. You can pause it now on your screen and solve it before you continue watching. Alright, so let me solve this also. Just arrange them. 1111 base 2. They have the same digits, so we'll just put them. Everything will go under their place value. Base 2. So you have to be very careful while doing this addition. It looks simple, but sometimes you can miss it. So 1 plus 1 here is 2. It's up to a bundle, so we drop 0 and carry it as 1. 1 plus 1, 2, plus the 1 we brought 3. So we have 1, 2, 3. This is a bundle. This is what is left. Drop this one. Carry that one again. 1 plus 0, 1. Plus the 1, 2. Another bundle, 0. Carry it. 1 plus 1, 2. Plus the 1 we brought, 3 again. 1, 2, 3. 2 has formed a bundle. We drop the one that is remaining. So the one we carry to this side, there's nothing to add here again. So we'll drop it here. So the answer is 11010 base 2. Now, did you get that right? Okay, if you got it right, bravo. Okay, let's look at this random question, still on that number basis. Right, I decided we should solve something like this because I consider it a little more complex than the ones we have solved. So we are given if 653 base 8 plus x44 base 8 equals to 1217 base 8, find x. Alright, so quickly I would like us to look at this. let's say, okay, we understand that we add this two. These two are added to have this. Just like you have 2 plus 3 equal to 5. And let's say you didn't know this one. So how you will get this one will be 5 minus this one. So we can change it to arrange it like that. That would be therefore 3 that we are looking for will be 5 minus 2. So that's the same idea we are going to use here. Alright, this is where the unknown is. We have to find x. So x is here. Make it the subject. So therefore x equal for base 8 equal to 1217 base 8. And this one comes inside becomes minus 653 base 8. See that? So when we do that, we can take this to the subtraction of number bases. And whenever we finish, when we have our answer, we use the comparison of the place values to know what the value of x is. So we can put it like 1217 base 8 minus. Always remember to arrange according to place value. Unit digit should go under unit digit. 10 digits should go under 10 digits. And the 100 digits should go under 100. Also base 8. So you do this. Alright? Okay. 7 minus 3 is 4. 1 minus 5 cannot, so you come to borrow 1 here. And pay attention to this. Since we are dealing with base 8, the one you are coming to borrow is coming as 8 items. It's coming as 8 items in 1. So it's coming as 8. Adds up here, gives you 9. Now 9 minus 5 is 4. Because you've taken 1 from here, 1 is left here. 1 minus 6 cannot. You come to borrow this only 1. So it's coming as 8 items again. Added to that one gives you 9. 9 minus 6 is 3. So what you have is 344 base 8. So by comparison, this is the place value, this is the similar place value, the similar place value. So by comparison, you say therefore x equal to 3. That's how to solve this kind of a problem. Okay, let's look at this other one. If 32 base x equals to 10100 base 2, find x. So what do we do? On the right hand side, we have the number to base x. Don't know what the x stands for, but we have to find that x. Right, that's on the left hand side. On the right hand side, we have to find we have a number to base 2. So we are going to, they are not like bases, so we should convert them to a central base, base 10, so that both of them will be in base 10, base 10. Then we can now use comparison of place values to know the value of x. So let's start converting both sides to base 10. This is power 0, power 1, power 0, 1, 2, 3, 4. Remember that. Alright, so what do we have there? What we have there is that. So start the, remember this is the linear method. Whenever we are converting from any other base to base 10, we use the linear method. So do it for both sides. So that will be 3 times x to the power 1 plus 2 times x to the power 0. Right? Equal to 1 times 2. It's always the digit times the base, then rest to the power that was there on the digit. Wherever you have zeros, just abandon it, because at the end of the day, everything we multiply by 0 will give you 0. Just take the next significant digit, which is 1. So 1 times plus 1 times 2 to power 2. So here we have x to the power 1 is still x. X times 3 is 3x. Plus x to the power 0 is 1. 1 times 2 is 2. Equals to 2 to the power 4 is 16. Times 1 is still 16. 2 to the power 2 is 4. Times 1 is still 4. So we have 3x equal to 16 plus 4 is 20. When this 2 comes, become minus 2. So 20 minus 2 is 16. So we have 3 is 18, sorry. 3x equal to 18. Therefore, x will be equal to 18 divided by 3 will give you 6. So that's how we know that our x is 6. The value of x is 6. So we leave today's class here. Thank you for watching.